Hello everyone and welcome back to OpenGL. Today we're going to be just doing a quick video on improving a few of the aspects about our shadow algorithm. So far we have a functioning shadow algorithm and it looks really broken, but the shapes are there, the shapes look right, but we see there's a bunch of patterns here that do not look right at all. And a lot of these problems that we're going to see arise from the fact that we are mapping a view onto a texture, and that texture has a finite resolution. If it had infinite resolution, that would be perfect. However, because it has a certain number of pixels, it can't have every point represented completely accurately. But there are a few improvements that we can make that will allow us to kind of obtain something that looks a little more realistic than that. So the first thing that we see is something called shadow acne, where we see that striped pattern. And the reason why this happens is because, so this is acne. I'm not here to sell you acne cream. This is just has to do with shadows. So let's say this is our directional light right here. Like that, and then let's say that we have an object right over here, and this has the light continues on here, and let's say this is the only object in here. This is our plane per se. So when the light hits here, the program will read it and it will map it as this is the depth value. Now it maps it to this coordinate right here. So since we have a finite resolution, we can consider this thing 1 pixel. We can't have something for every fragment. It can only be so sharp of a resolution. And this continues. So we have this, and then wherever this continues to something like over here, where it's like that, and this is another pixel, and then we have another one. Now when we look at when we take the coordinate from each fragment to determine if it's in the shadow or not, we convert it to an integer or into a normalized coordinate, and each normalized coordinate will map to some integer pixel coordinate on the image. So each one of these values here, so let me just zoom in a little bit. This singular pixel right here, I'll just draw it again over here. This is a pixel. I'll draw this in red actually, just to make it different. So this is the texture. This is our depth map. And once again over there, and so on. So each one of these, everything here will map to this pixel right here. So everything between here and here will map to this pixel coordinate. Now everything between here and the part where where the visual coordinate intersects with the surface will be rendered as not in the shadow, because the depth here, these depth values, according to the directional light, or let me just make this, oops, that's not what I wanted. This is our sun. So according to the directional light, the depth values of these fragments right here are greater or are less than the depth value in the coordinate, and that corresponds to everything here. So everything here will map to, just a reiteration, everything in between this point and this point will map to this red texture coordinate here when we take the projection coordinates. Now everything over here, according to the depth map, will have a greater depth value than what is stored in the texture. So therefore, these will be rendered in the shadow. So we get a striped pattern, and that continues on throughout every surface. So that's why we see there's some that are normal colors and then others that are not. So it creates a striped pattern that is almost epilepsy inducing, or seizure inducing rather. But there is a way to actually fix this, and that's using something called a bias, and this is where we just offset it essentially. So if we were to, once again, if this is our light, let me just draw this in yellow. So this is our light here, and our object is like this. We're going to have the pattern where something like that. So all we want to do is essentially just offset the object in the fragment shader, only in the shadow calculations, by some value where everything is accurately determined. So this point, which was in the shadow, well, which was previously in the shadow, now is offset to this point, which is not in the shadow, so it renders its regular color. And this is called the bias. So this amount here is the bias, and it looks pretty good. However, this doesn't work for you can't have a single value for the bias, because the angle between the light and the surface has to actually, or will change. So you have to change the bias accordingly. So for example, if we had a different surface that was let me just draw the same light ray, and then we have a different surface here that's the angle is larger, then our texture looks the same, something like that. And we were to offset it the same way, or the same amount, this would not produce the desired result, because there still would be some of this that is still in the shadow. So as the angle increases, we have to essentially increase the bias, and we can do this using a dot product with an upper and lower bound, and the math that we're going to do is related to the normal. So let's write this code now. I'm going to go into object.fs, the fragment shader, and I'm going to go to the function calc dirlight shadow, and the first thing we're going to do is we're going to take two parameters. We currently take none, but we actually do need to take two. So the first one is just vec3 norm, and then vec3 light direction. The normal will be the normal vector of the surface. Now what we want to do is go to the bottom, and we're going to take a bias here. So we'll calculate the bias first. So calculate bias. So float bias is equal to the maximum. So we're going to have a maximum value of, say, 0.5, and we can actually just we'll just have float max bias is equal to 0.05, and float min bias is equal to 0.005, and then we'll say float bias is equal to the maximum of max bias times, then in parentheses 1.0 minus the dot product of the normal and the light direction, and then the minimum, and then the other value will be min bias. So what this does is we're taking the dot product between the normal and the light direction, and because the normal value is perpendicular, oops, that's not what I wanted. Oops, there we go. So the normal value, or the normal vector here, it looks like this. What is up with this marker thickness? And that's perpendicular to the surface. So the dot product between the normal vector and the light direction will be inversely related to the dot product of the surface with the light direction, just because they're perpendicular. So that's why we're doing the 1.0 minus. And this can be a maximum, the dot product can be a maximum of 1. So if we do, so it'll be bounded between 0 and 1. So it'll go from 0 max to 1 max, anything in between. And then we just take the maximum of that product with the bias, or with the minimum. So that's the bias. And then what we now want to do is return current depth minus bias is greater than closest depth, and if that's true, return 1.0, otherwise return 0.0. So we're essentially just subtracting the bias from the depth value in the texture. So instead of moving the surface up like we do here, what we do in the shader is we take the, oh, why is this so thick? There. We take these values and move them up by the bias. And then we compare these. Alright, so now this, when we run this, this should not, we should not see a striped pattern anymore. Oops. I did not pass in the parameters. So now we actually have to pass in the proper parameters to the directional light shadow function. So just pass in just norm and light direction, which we calculate in the calc dir light function here. So let's run this. We see there's no striped pattern anymore, because once again, it's all biased, so it's offset just by a little bit. Alright, the next thing that we want to look at is something called oversampling. So let me just run this again, just so I can show you what it is. Oops, that is not right. Alright. So oversampling, what it's going to aim to solve is this problem right here. So we see once again this arises because of the finite resolution. It's all pixelated, and that's, we can't really do much about that because it's a texture. Once again, it doesn't have infinite resolution. We could increase the resolution. So if we go into where is it? If we go into light.cpp and look at the shadow FBO and initialize it with the larger resolution, we should see that it's less pixelated. And yeah, it looks a little sharper, but you can still see the pixels. So the best way to solve this is actually to do something called blending, not in terms of transparencies, but it's called PCF, where we're gonna, which is percentage closer filtering. And this, what this is going to do is we're just going to take the values from the neighboring coordinates on the texture and determine if they are in, and we're just going to kind of average all 9 values. So this will also be in object.fs, and what we can do is we're going to, the bias calculation remains the same. Then we're going to do PCF. So we'll have a float shadow sum is equal to 0.0. Then we're going to calculate a 2D vector, so vec2 texel size, so this is just texture pixel size, is equal to 1.0 divided by the texture size of dir light dot depth buffer, and 0 is the second parameter there. And then we're going to essentially just iterate from -1 to 1 in both directions, and just calculate the average. So for int y is equal to -1, y is less than or equal to 1, y plus plus, and the same thing for x. So for int x is equal to -1, x is less than or equal to 1, x plus plus. Then float PCF depth, we're just going to get the depth value of the neighboring texel. So PCF depth is equal to the texture. We're going to call dirlight.depthBuffer as a texture. The coordinates are going to be proj coords, so the projection coordinates of the current fragment, .xy, then plus the vec2 of xy. So we're just creating the offset by -1, 0, or 1, and then multiply the vec2 by texel size. So we essentially just convert the offset in pixels to the offset in normalized coordinates. And then we just want to get the R value from that texture because once again it's only one component. And then we just add it to the shadow sum. So shadow sum plus equals the same calculation as before, current depth minus bias is greater than PCF depth, and then question mark 1.0 colon 0.0. So this is the same ternary operator that we had before. And now we're just summing it across 9 values, and then we want to return the shadow sum divided by 9.0 to get the average. Alright, if we run this and we look at the texture, you can see that there is some blending. So it's not just in the shadow where it's not. There is a little bit of blending, and this will really help at farther distances where you can't pick out the pixels as well. But once again, this is just a very basic solution. There are other ways to help this, and you can also think about linearizing, which I will definitely look into. See if I can figure out a way to kind of linearize the pixels here to make it less of a pixelated map. Alright, so those are the two somewhat related things, and now the last one is actually about the bounds of the image. And this is called oversampling. I think I called PCF oversampling, but this is actually oversampling. So with our directional light, we have what's called a bounding region, and that bounding region defined essentially our shadow box and the range of values that we would consider shadows for. And what about stuff that's not in that box? So if we had objects that are outside of the box, and once again this is just finite because we don't have infinite memory, we just have to have a finite value here. So since we have a limited range, we essentially have to deal with the cases that the fragment that we're looking at is not in that box. So this would mean figuring out what to happen on the border, what to happen if it's too far away, and this math the numbers will make sense once we write the code. So the first thing we're going to do is in framememory.hpp, and we actually are going to fbo.allocate an attached texture, we're going to set unique parameters here. So for text min filter, we're going to have GL nearest. Text max filter, we're going to have GL nearest again. And then now for the wrap values, we're going to have GL clamp to border. So just pass those in for the last two. And what clamp to border does is, if we try to sample a coordinate that is outside of the normalized range, so outside of 0 to 1, it's just going to return the border color. And now we actually need to set the border color. And we can have a float array here, so float border color array is equal to a value, and we're just going to have it as white. So 1.0, 1.0, 1.0, 1.0. And the reason why we're doing it as white, because if it's black, then it would be considered in the shadow, because a depth value of 0 in the texture would mean that the closest object is right on the camera, is exactly on the camera or on the light. So we just want to set it that there's no objects outside of the shadow box. So nothing will be rendered in the shadow when we're looking at the shadow box. And then we just need to set this with a GL text parameter FV, and then pass in GL texture 2D as a target. The name will be GL texture border color, and then the parameters will be just border color. Alright, we can run this. I don't believe we're going to see a difference, but let me actually do this. I'm going to comment this out just for a second, just to show you what it would look like if we had a small bounding region in terms of X and Y. So I need to go into... Alright, so I'm going to go into main.cpp, and I'm just going to decrease the bounding region box to just -5 to 5. So now if we run this, you see that this is essentially the box. This is the shadow box that the light considers, and everything outside is rendered in shadow because the depth value in the texture is 0. I actually have no clue what this is. I have 0 clue what that is. But anyway, what we can do now is if I uncomment that code in frame memory and actually set the border color and then run it, it's just running. Everything that is not inside the box will be considered not in the shadow, and we don't see any of the little box or of the cube shadows because those aren't in the smaller shadow box. So once again, we just set the border color to white, so it's like there's nothing that the directional light can see. So I'll reset the values so that we actually get the cube shadows in there. Come on, where is it? Here we go, like that. Yeah, so we have the cube shadows once again. Alright, that's good. Alright, so that's that. Is that it, actually? Oh, so yeah, that takes care of the X and Y direction, but now we actually need the Z direction. So we've taken care of the conditions where it's too far left or right or up and down, and that's pretty easy to fix just with the border. However, with the Z coordinate, if it's too far away from the light where it just doesn't see it at all, the texture will have a depth that, so if the depth value in the light space is say 2.0, and that's just outside of the bounding region frustum, what's going to happen is it will be considered in the shadow at all times, because the texture can have a maximum value of 1.0, and that's just how the colors work. It goes from 0 to 1 normalized. So 2.0 will, as a depth value of 2.0, will be greater than what the texture has, which is 1.0. So even though it doesn't consider that there is anything beyond it, that 1.0, or even though it doesn't see anything in front of the further object, it will just still say, okay, there's an object there, or there's an object exactly at the end of the bounding region. So we just need to say in our fragment shader, where is it? In calculator light shadow, we're going to have here, after we calculate the projection coordinates, and before we calculate the closest depth, we're going to say if projcords.z is greater than 1.0, return 0.0. And this just means if outside, or if too far from light, do not return shadow. So 0.0 just means 0 shadow. So if I were to, well, I'm going to comment this out first actually, just show you what it would look like with a minimized bounding region. So we'll say the z coordinate of 0.5 to 1.0, and we'll see what the value looks like. Everything is pretty much in the shadow because it's too far from where the light is. Now if I'm going to turn, when I turn the actual, this bounds checking here on, we're going to see that everything that is beyond the range is considered, what is this? Okay, this is weird. I don't know what that is. But this is considered not in the shadow because it's too far. Okay, I think this is, I was thinking that this may have been a problem. Where did it go? Oh, it's over there. Okay, I think this might be one of the problems with the PCF. I don't know, I'll do some experimenting, but I could be wrong. Alright, well, I'll just go back to the normal bounds and it won't make a difference. And everything is there. Everything looks good. And this looks a hell of a lot better than it did last time, where it was actually inducing seizures. But anyway, yeah, that's a little bit of a shadow improvement. In the next video, we're going to be actually doing shadows with spotlights, and then we'll do point lights from there. And spotlights are actually somewhat similar to directional lights. But until then, enjoy yourselves, and I'll see you then. Have a good one.